Okay, our next talk is by Pamela Burnley at the University of Nevada. Pam, if you can share your slides. And the title of her talk is In-Situ Measurements of Deforming Materials, Synchrotron X-ray Diffraction and Radiography Combined with Ultrasonic Interferometry. Thank you.
Hi everyone, thank you for having me. I'm actually going to turn off my camera for the talk to try to improve my bandwidth. But I'm actually Taryn Traylor. I'm a graduate student working under Pamela Burnley, and I'll be giving this talk on behalf of Pamela, and she apologizes for not being able to present today. So this talk will discuss some of the work our group has done investigating deformed polycrystalline materials using synchrotron X-ray diffraction and radiography, in addition to some work that has been done in combination with ultrasonic interferometry. First, I'd like to acknowledge the funding sources for our group and the beamline we use, as well as the beamline scientist, Haiyan Chen. So in our group, we're looking at polycrystalline systems with an eye towards better understanding how their bulk behavior relates to the single crystal behavior. So today's talk will discuss how the synchrotron has advanced our understanding of complex polycrystalline materials and how we perform experiments using synchrotron X-ray diffraction and ultrasonic interferometry. And I'll also discuss some of the data analysis procedures we use and the results from a few different experiments. So 20 years ago, pre-synchrotron, people studying rock deformation focused on the boundary conditions, measuring the load and the strain, and treating the interior of a rock like a black box, where microstructural analysis post-mortem told us that this black box was complex, but it did not tell us how. And so the synchrotron now gives us an entirely new stream of information regarding what is going on inside polycrystalline materials. And so as a reminder, polycrystalline systems under deformation are fairly complex. This illustration to the right shows a polycrystalline aggregate where even for a monometallic phase aggregate, you have grains that are all oriented differently. And then these sets of lines inside the grains remind us that the crystal lattice is oriented in different directions and that we're going to have slip planes in each grain that are oriented differently. So if we look for the boundaries of the polycrystal, as we often do, and we apply a stress, we want to know how does the polycrystal decide on its aggregate behavior. Polycrystals are elastically anisotropic and they're also plastically anisotropic. This top left-hand figure here just shows a diagram for the anisotropy of the Young's modulus for single crystal microcline. And this just shows us that depending on the crystal orientation, the elastic modulus will have a different value. And so even for a single phase aggregate under deformation, things can become complicated. And when you introduce more than one mineral phase, there's an increased level of heterogeneity, which leads to more complexity. So I'm just going to talk briefly about our experiments utilizing synchrotron X-ray diffraction to learn about high pressure deformation. Don Weider mentioned this setup yesterday, but just as a reminder, we perform these experiments at the Advanced Photon Source at Argonne National Laboratory. And we use the multi-anvil apparatus, the D-dia, that sits on a large hydraulic press that provides the pressure conditions. And this is located at the APS 6B&B. Within this D-dia module, we have our cell assembly. This is a schematic of the hybrid D-dia ultrasonic cell assembly with our sample of polycrystalline material in the center. Recently, we've added the use of ultrasonics, incorporating the diascope system to monitor our samples while we're deforming, allowing us to obtain the travel times within our sample. So using synchrotron white X-rays, we can also measure the length of our sample during deformation, and we can measure the lattice spacings within the sample with an array of energy dispersive detectors. We can then interpret our diffraction data using elastic plastic self-consistent modeling. So looking a little more into X-ray diffraction in a polycrystal, polycrystals, as I mentioned, have lattice planes that are diffracting. And as the diffraction peak shifts in response to the stress states of the groups of grains contributing to specific diffraction peaks, this gives us a way to look inside the polycrystal at what's occurring. So in an energy dispersive setting, we can have a plot like this where we have our intensity for our diffraction peak as a function of the d-spacing. And this is just showing that during uniaxial deformation, in the transverse direction, so diffraction that's collected from the detector at 90 degrees, the d-spacing is going to increase, while diffraction planes that are oriented normal to compression will shift to a smaller d-spacing. So digging a little more into what's actually going on in the diffraction and what's making up this diffraction signal. Here we have our sample. This is just a simplified schematic, but we're looking at grains that are oriented with their lattice planes perpendicular to compression. And these grains are being collected by detectors along the compression direction, so detectors 1 and 9 here. And we're also looking at planes in the transverse direction where we have those planes aligned along the compression direction. Those are being collected by the detector 5. And so for energy distorsive X-ray diffraction, we have our X-ray beam coming in, it diffracts inside the sample, now it comes to diffraction. So in this group of subgrain populations at the top here, which sends the signal to detector 1, we're looking at grains that have lattice planes with varying D spacings that are roughly normal to the compression direction. And so when we look at the X-ray diffraction pattern, we see many peaks where each peak correlates to a specific group of grains that have the lattice planes perpendicular to compression. Similar is the case for the transverse direction. We get a diffraction pattern with multiple peaks where each individual peak is correlated with a specific group of grains. And so each diffraction peak comes from a different grain population, which is sampling a different aspect of what is going on inside the polycrystal. So the population of grains that are in the X-ray diffraction peaks aren't completely homogeneous depending on where we look at them. This diagram is just showing the relationship between the diffraction geometry for grains contributing to a given lattice reflection and the orientation of slip with those grains, within those grains. And so for diffraction in the compression direction, all grains contributing to a lattice reflection will experience the same resolved shear stress because the angle between the slip plane and the loading direction is going to be constant. But for diffraction in the transverse direction, the group of grains that are selected by diffraction to be in the same diffraction peak can actually have a variety of resolved shear stresses. And so the complexity of this diffraction data requires an interpretation technique that can make the maximum use of this data. And so as I'll discuss next, when we forward model our diffraction data, we tend to focus on the modeling of the diffraction data from detectors in the compression direction, as our data is typically much cleaner. And so elastic plastic self-consistent modeling provides us with the ability to analyze data a level more comparable to the complexity of our diffraction data. Lal touched on this earlier, but just to reiterate, these models look at each crystal's role in a polycrystal as an inclusion in a homogeneous elastic medium. And as each crystal is loaded by the medium and deformed, the model then uses Eshelby's solution for an elliptical inclusion to solve for the strain, which is compatible for the crystal in the matrix. And so since the elastic medium is an average of all the grains in the material, this has to be calculated iteratively. So as each crystal is loaded, this information is averaged back into the homogeneous elastic medium. And so this allows us to have different stress states for different crystals, depending on how they're oriented in their elasticity and plasticity. So this EPSC forward modeling technique was developed by Carlos Tomé and Born Clausen, among others, interpreting neutron diffraction data. And what they do is forward model the material and then adjust the slip system parameters to match their observations. And so the input for this model includes the boundary conditions, whether it's stress or strain, a list of grains in the material and their orientations, single crystal elastic constants for the material, and the active slip systems with the critically resolved shear stress and the hardening parameters. So the model takes all this information and increments the boundary condition chosen, and the code runs through and calculates the stress and strain for each crystal. So the model continues to iterate until a consistent solution is found. And then the model output for the EPSC model is the macroscopic stress and the elastic and plastic strain for each crystal. And the code that we're using was provided by Carlos Tomé at Los Alamos. So I'm just going to discuss a few experiments where forward modeling was done on olivine X-ray diffraction data. And I just want to note that olivine has 8 slip systems, but due to their arrangement, they do not provide a closed yield surface. So in other words, there are some grain orientations that are not suitable for any slip system. So this is just an example of starting out with EPSC modeling for phaelite. This is a graph showing the lattice strain on the vertical axis, which is just the change in despacing relative to the first diffraction data point. And this lattice strain is plotted as a function of sample strain. The lines on the plot are the EPSC model, which correspond in color to the diffraction data here as the data points. And so if we use the slip systems only for olivine in the EPSC model, we can see that the model does not match very well. The EPSC model is work hardening while the diffraction data is not. And we can also see that the peaks are not in the same order for the model and the diffraction data. We have our 002 peak at the top and our 002 reflection lower in the order. And so if we add kink band formation, which is the low temperature accommodation mechanism, we can target the grains with kinks, which tend to have their 001 axis parallel or near to compression, and we can soften those grains. And so this is just some EBSD work that was done on magnesium germanate olivine grains, where we can see this kink banding. And this is just another micrograph showing the similar kinking. And so when we include the slip system combination and kink band formation into the model, we're able to match our diffraction data much better. And so this experiment on phthalate was performed up to about 15% strain, but we wanted to investigate more of what was going on at low strain since we did not get much information out of the strain beyond about 4%. So we started doing slower experiments where we are able to focus early on in the deformation. And this allowed us to produce or perform multiple experiments in a single day at varying temperature conditions. And another point of interest for these experiments was that we wanted to understand why we were getting failure elasticity at the higher temperatures. This is something Nadej Hilaret also saw. And so this was a multi-segment experiment performed up to about 4% strain on polycrystalline San Carlos olivine from about 440 degrees Celsius to about 1100 degrees Celsius, with the pressure conditions just changing slightly as we're increasing in temperature. We have our powder diffraction data shown as the symbols with the diffraction from the detectors in the compression direction in the upper quadrant and the diffraction from the detectors in the transverse direction in the lower quadrant. These EPSC models are shown just as the solid lines again, correlating with the color of the diffraction data points. And here we have our EPSC model just showing the elastic slope of the aggregate only. And we can see as we increase in temperature, the material is not behaving elastically earlier in the deformation, even in the first strain increment. And so this made it difficult to model the diffraction data. And so we created a slip system used in the EPSC model that would allow us to have a Schmidt factor that was the same for all the grains in the early part of the deformation that would allow us to manipulate this elastic slope. And so we created this fake slip system to mimic this unknown deformation mechanism, where the figure to the right here is just the slip system with the 30 planes and directions, which allows us to have every grain population to have the same Schmidt factor. We can then use the work hardening parameters to model the slope at the beginning of the EPSC simulation. And as we continue deforming, the strain increases, and at some point, the slip system will turn off. And so here's just the first from the suite of experiments I showed just a couple slides ago. This deformation experiment was performed at 3.8 GPa and 440 degrees Celsius. And again, we're just showing the EPSC model pure elastic slope. What we see is that the elastic slope does match the first 2 to 3 diffraction data points. And as we incorporate the fake slip system to the model, we're able to get that curve to now bend over from after those 2 data points. And now we're able to match up to about the first 5 diffraction data points. Then as we add in the slip systems of olivine and kink banding, we're now able to get those curves to flatten out and overlay the data much nicer. So here are the EPSC models for all 4 experiments that I showed earlier, and we can now see that we're able to match the early diffraction data as we increase in temperature. So these figures to the right show the critically resolved shear stress as a function of temperature for 001 slip on the upper figure and 100 slip in the lower figure. The 4 data points on the graphs are the critically resolved shear stresses that were obtained from the 4 deformation experiments I showed on the previous slide. And these are overlaying the curves from single crystal experiments by Durink et al. This data basically just shows that the EPSC model output is matching the literature values for the critically resolved shear stress for slip systems in olivine. And this just gives us further confidence in our EPSC modeling strategy. So I want to transition into the experiments where we've incorporated ultrasonic interferometry, where we're now able to also obtain ultrasonic travel time measurements while we're deforming using the Diascope system. So as I mentioned, we've added ultrasonics as a probe to our experiments, and this basically just allows us to now look at how differential stress impacts the compressional and shear wave velocities of our material that are propagating along the compression direction. So this schematic to the right just kind of shows the orientation of everything. We have our loading direction in the vertical direction, and we have our waves propagating along this direction. And so this dependency of wave velocities on the stress state is known as the acoustoelastic effect. And this technique is used in metallurgy to measure the stress in situ at ambient to very low pressures. And without going into too much of the theory, it's been shown that the change in wave velocity is proportional to the stress state, the uniaxial stress state, through these proportionality constants, Aij, these acoustoelastic constants. So by using EPSC modeling to derive the volt stress via the diffraction data, we can then plot the wave velocities in our experiment as a function of the stress state to obtain these acoustoelastic constants. And so this figure on the left just shows the percentage of wave velocity change as a function of the macroscopic stress for an experiment performed at 9.8 GPa and 650 degrees Celsius, where we took measurements during differential ram advancement and during a differential ram retraction, maintain the same strain rate. And we can see that the acoustoelastic slopes during the advancement to the elastic limit, which is shown as the black data points, follows a similar slope to the retraction data in both the P wave and in the S wave data. And we're seeing about a 0.5% of wave velocity change per GPa stress for the P wave velocity data, and about a 0.2% wave velocity change per GPa stress for the S wave data. On the right, we're plotting these acoustoelastic constants, the P wave A11 acoustoelastic constants and the shear wave A12 acoustoelastic constants as a function of pressure and temperature for multiple deformation experiments that were done on olivine, San Carlos olivine. And what we see is that we observe a minor pressure dependence in the P wave data, and we're not really seeing much of a temperature dependence. So since these are the first measurements of the acoustoelastic constants at high pressure, we don't have any comparable measurements to compare our results. And so it's informative to make some form of comparison. So we've done this with measurements of metals at low pressure. And so most measurements in the literature report the third order elastic constants rather than the acoustoelastic constants. And so we calculated the P and S wave acoustoelastic constants as a function of the second order elastic constants reported in literature. So we have our lambda mu and our Moynihan third order elastic constants L, M, and N. So these figures just show the calculated P and S wave acoustoelastic constants of various materials from the literature as a function of the bulk modulus and the shear modulus, in addition to the polycrystalline olivine samples I previously showed. And so this upper figure, we have a logarithm decrease in the bulk in the acoustoelastic constants with P wave as a function of bulk modulus increase. Here we have these red data points indicating rock data from the literature. And what we can see is that they're scattered at lower bulk moduli. These are experiments that are done at lower pressures, confining pressures. And we can see that our samples of polycrystalline olivine are plotting in the range of other metallic material studies that performed at lower pressures. So we have some steel alloys and copper and tungsten. Similarly, when we plot the shear wave acoustoelastic constant as a function of the shear modulus, we observe a decrease in the A12 acoustoelastic constant with shear modulus increase. And again, our polycrystalline olivine samples are plotting within the range of other metallic materials. And this isn't that surprising for us that the polycrystalline olivine samples are plotting with the metallic materials rather than these rock studies. And this is mainly due to the fact that the acoustoelastic response for geologic materials at ambient to low confining pressures is attributed to pore closure and microcracks, which we should not be as significant at our high confining pressure conditions. And so we can see that there's a clear relationship between these acoustoelastic constants and other material properties. And so in conclusion, synchrotron X-ray diffraction is a powerful tool for investigating internal deformation processes in polycrystalline materials. And in combination with EPSC modeling, we can derive a single microscopic stress for in aggregate, as well as the critically resolved shear stress for individual slip systems operating in a sample. And we can map these parameters across the entire PT space available to us in the DDIO. With integration of the ultrasonic interferometry, this gives us the ability to measure the acoustoelastic effect, which can provide another in-situ stress measure that can be used in experiments where diffraction is not possible, including offline experiments. And we may find that with measurements of other minerals, that the acoustoelastic effect may be useful in high pressure seismology and highly stressed parts of the lower crust and mantle. And that's all I had for you guys today. Are there any questions about our wave time?
We do have time. Thank you so much, Taryn. Sorry, I introduced you as Pamela.
No worries.
Okay, questions either via chat or by raising your hand. No, that's Stella. So I guess my question is, what would be the next thing you'd want to do? What is the next step in this research?
So I kind of touched on that a little bit. You know, we want to investigate the acoustoelastic effect in additional minerals that are important in the mantle. And additionally, you know, we'd like to try to set up an integrated system where we can form these measurements in offline experiments. So forming them in the Griggs, a deformation apparatus, perhaps. Yeah.
Other thoughts or questions? Are there specific minerals you want to look at next?
Yeah, we're hoping to look at diopside next, and then eventually, you know, we'd like to maybe look at quartz, perhaps.
Yan Bin, go ahead.
Yeah, I'd like to ask a question about the self-consistent modeling fitting in the lattice strain and stress.
Mm-hmm.
So when you show the figure with progressively higher pressure, higher temperatures, you use the additional kinking bands to fit the data. So my question is, did you involve the same number of fake you call fake slip systems throughout this temperature range, or did you have to change it? Is there any indication of the changing in deformation mechanisms because the temperature range is pretty wide?
Yeah, so I believe that we use kink banding throughout the entire temperature range, but I only performed a few of these experiments, but I believe that in most of the experiments, I think once we get to the 800 to 1100 degree range, we stop using the fake slip system.
And then the fitting, it becomes satisfactory above certain temperature?
Yeah, exactly.
Okay,
Yeah.
Okay, thanks.
Any other thoughts or questions? Caleb.
Have you started to try to apply this to polyphase systems, not just polycrystalline systems, but systems like granites, per se, or other kind of complicated rocks to see how that affects which slip systems are operating?
Yeah, we haven't yet. That would definitely be kind of towards next steps. I'm just starting my PhD, so it's definitely something to consider. We have enough time. But yeah, definitely something I think it's possible. You know, perhaps if we had EVPSC modeling, that might make things a little easier.
Any other thoughts or questions? Okay, thank you so much, Taryn. That was great.